Good morning. I think we can wait a couple of minutes because I expect more participants and then we can start the lesson for today. I think I can start. Then if someone's joining, it's appreciated. So the topic of today is the last topic of the course, which is also the last topic that you may be asked to answer during the examination, and it is about localization technologies. So I'm a technical, I have a technical background in telecommunication engineering with expertise in telecommunication and its application for localization purposes. So that's why I'm in charge of this thematic zoom of the topics in this course. And I would like to try to give you the idea of localization technologies limiting the technical content of the theory behind it. And I will try to share with you some different technologies and architectures that are existing nowadays and that can be applied along different stages of a production or a supply chain monitoring. So I will try to give, let's say, a contextual list and comparison of technologies, differentiating between satellites and network-based technologies. And at the end of the day, I will also give you some ideas or show you what is currently a hot topic in the industry. So in few months, you are expected to enter into the job market, and if you ever have to address these topics, you are somehow warned about the current discussion in the companies. Before entering into the details, I would like to start with a simple question, which is a question for you, and I ask you to reply in the chat of WebEx, which is a simple task. So, in your opinion, do humans localize? So, what is your first feeling, your first approach to localization? And as a human being, are we able or do we localize something? If yes, how? So please write in the chat how can perform localization as it would be. So no technology, just our human skeleton, body, senses, and all the parts that we have in our body. How do we use it for localization? So if you please write in the chat, or if you prefer, turn on the microphone and reply to this simple question, because it's really the starting point and the connection between humans and technologies. So no fear, you're not going to be evaluated at all. Just write in the chat your feeling about localization for a human. Visual localization, with visual you mean using our eyes, I guess, and the answer is definitely correct. Other ways, because that's not an exhaustive answer. I mean, it's a piece of the full problem, but that's definitely true. Exactly, also sound, so using our ears to localize something. And actually, the direction of this answer is we need to use our senses. But actually, we can do much more than be, visual and sound. So we have eyes, and we can use them to find or to understand the angle and the distance of what we see. Similarly, also our ears can more or less understand the direction where the sound is coming, and with less accuracy also the distance. So we can say, okay, that music, that specific sound is coming from that direction and is more or less close or far to me. And also, we can also use the nose to smell possible flavors and understand if they are close or far with respect to our face. And this utilization of senses to detect and know more or less the angle of the distance is exactly what technology would like to imitate. So the positioning technologies, localization technologies we are going to see today are exactly imitating the human senses. And some of them are able to estimate the distance only, some of them are able to estimate angle and distance, some of them are more accurate than the others. So overall, there is a variety in the type of information that a technology can measure, just like our senses measure. They also have different accuracies, but overall, they are all functional to perform localization. And an important aspect that I would like to emphasize is that this information is a relative information, in the sense that what we hear, what we smell, what we see is, let's say, measured or is related with respect to our face as a centric point. So all the localization information is relative with respect to myself. It's not an absolute localization, it's relative with respect to where I am right now, so where my face is right now. And given this, let's say, quick, fast introduction to localization, let's now move into daily use of this type of technology. So I believe that 99.999% of you is using at least one localization technology, or it's hiddenly using a localization technology for a specific service. So which are, in your opinion, daily life applications that are related to localization? You can think about your personal experience as a consumer, or you may also think about use of localization in industry. So also in this case, please write in the chat what you believe is localization today, what are the applications that benefit from it. So in which cases it is good or it's convenient to localize by understanding the distance or the angle of something in practice. So even if you're not familiar with the technicalities of the technology, you are, let's say, skilled enough to use or you daily use ICT technologies, and many of that is based on localization. So where do we find localization in today's 2026 services? Obviously, if we are navigating in the web, we do not need localization at all. But there are other super important and are largely common applications that are based on localization. And you are saying tailoring products or services according to specific customer segment. Exactly. So understanding the geographical area of a Google research or understanding if the internet traffic comes from Italy, Europe, China, United States, whatever, is, let's say, a way of localizing something. In that case, localization is the geographical area, so it's not a specific high accurate identification of where the user is, but still, it is an application of localization. Put yourself in the mindset where instead of your face with the different senses, you have a technology, and that technology is able to understand the distance or the angle of what's in the surrounding. Do you have any idea of something working like that? Or imagine what you do with your smartphone. One or many of the most important or most commonly used smartphone applications are based on location services. Which one? You can think about social media. You can think about default apps inside any smartphone. Global Uber, yes. So now we are still in geographical localization. Interface language, yes. But Global and Uber are also relevant examples for a different perspective because Global and Uber are based on not super accurate, but still accurate localization service because you need to specify to Globo where they have to deliver your product, and Uber has to know where you want to go and where you are right now, so where to pick you and where to drop you off. And also Uber is important because it uses location services in the middle. So from the starting point to the end point, the Uber driver has to navigate over a map. And navigation is the most common and the straightforward example of where do we currently use localization technologies. Also in Glovo, by the way, because the Glovo driver picks your product in the shop and typically follows the maps, so a navigator to bring it to your specific house. So these are examples of daily use of application related to localization. Would have expected something like this. So these are my guesses on your possible answers. I'm not completely right, but I would have expected in your answer, for instance, mentioning about GPS technologies. Maybe some of you are familiar with RFID. We will see it later. Or other types of sensors, such as camera, radar, and LiDAR sensors. Smartphone and car is mainly for map navigation, but some of you might also have mentioned warehouse management or identification of the supply chain stage, so tracking the products all over the supply chain. And other, let's say, application-oriented cases are instead, for instance, guidance in the hospitals or route navigation, identification of possible intruders in monitor areas such as our houses, localization of keys, so we can understand where we lost our key with the AirTag or other similar product. Find My Phone, by the way, is still a localization service that is available in our smartphone and allows to recover its position in case we lost it. Monitoring civil infrastructure, so detecting if they are slightly deviating from day by day, so they are possible leading to a collapse. Tracking animals, so nowadays there is an increasing demand for dog or cats or whatever pet tracking, so we would like to know where our dog is any time of the day. In case you are, let's say, sport addicted, one of the most common application is Strava, and it's still based on finding the route or checking what we have done with our bicycle or with our running activity. So this is just a simple, short list of applications that have somehow to deal with localization, no matter what is the technology behind it. So this is just general. So let's now jump into more practical frame of our mindset. So the the key question, the key demand that we need to deal with localization is localization of ourselves, or in a typical industrial user case, we would like to know where a specific object or a specific asset is. And this seems a little bit trivial, but from an industrial perspective, it has a huge importance, because typically a new product, a new device, a new object that is purchased by our company or also by ourselves in our home is highly attractive at the beginning, but day by day, week after week, it starts to lose its appeal. I mean, it's natural. So when you buy something, you are excited about it, but the sooner you use it, the more you lose its appeal. And at the end of the story, after some time, you forget about it at all. And from an industrial point of view, losing or do not knowing where that specific object that maybe costs a lot of money is important. So allowing the recovery of that specific unused product can be a cost saving for the company. Or the company would like to know where the bunch of product is any time of the day, or would like to understand if something has been lost somewhere in the plant or wherever it is. Knowing the location of devices or also human workers can allow the triggering of its activity in proximity of devices. So in case, I don't know, you have a specific product, I mean, you are a worker, you work in a production plant, a specific product can only work in limited, constrained, authorized area. You need to authenticate and activate the device all in that area. So it's location-based triggering of device utilization. Knowing the location also allows to cross-check the workload by authenticating the stages of the production. And it's also a confirmation that a specific activity, a specific operation on the product has been done there in that machine at that time of the day. This is also useful in case you are hypothesizing a possible anomaly in the production. So locating where the anomaly could have been happened is an implication of localization. And also the final example is knowing what happens in the transport. So knowing the location of your truck or your train, whatever you use for shipping, is a way where localization assists the full production. So given this hint or idea on where we can find localization, let's now enter into the technicalities of the most commonly used technology, which is the satellite one. So satellite technology means global navigation satellite systems. And the GPS is just one of these satellites. So a technology that performs localization by using orbital satellite. So around our Earth, we have thousands, hundreds of satellites that are orbiting around. And these satellites are used to estimate the position of devices. So our smartphone, when we have the activation of the GPS, is exactly receiving a wireless signal that is sent from these satellites and used to estimate the position of our device. Overall, the family of satellite system is GNSS, but then we have specific names for specific implementations. So GPS is one of them, and it is a system that is active since 30 years. Then we have the, let's see, the relative versions of Russia, China, India, and European Union. So these are just examples of constellation of satellites that are orbiting around our planet and provide the position performance every time of the day in any position of the planet. And how does it work? It works by a receiver, which can be our smartphone, our vehicle, or whatever device that is able to detect the signal that is sent from the satellite. And by knowing the time at which this signal is received and the time at which the signal is transmitted, the device estimates the distance. So it estimates the distance between satellite 1, the distance with respect to satellite 2, with respect to satellite 3, etc. And by intersecting this ranging information, it is able to understand where it is in the Earth. In order to estimate the position, we need at least 3 distance information. Maybe I explain with the next figure, then I go back. So by intersecting at least 3 ranging, we are able to understand the 3D position of the device on the Earth. Because the intersection of 2 circles is 2 points, while the intersection of 3 is a point in 3D. And the position is not ambiguous. Then you also need a 4th additional satellite in order to also estimate the time difference, so the clock difference between our device and the satellite, but that is just a technicality. So in order to get 3 coordinates, we need at least 3 satellite information. Then, in order to make the system work, we need 4, but that's because we do not have only to estimate x, y, and z, so 3 coordinates in the sphere, but we need also to estimate a 4th variable, which is the difference in the clock. So in order to get on our smartphone the location pin of where we are, we need at least to receive 4 satellite information simultaneously. So this means that out of all of these orbiting satellites, right now we need to get at least the signal of 4 of them. Then in a couple of slides we will see that we see much more, but that's the main minimum requirements for making GNSS working. So at least 4 satellites that are simultaneously visible from our side, but the number of satellites for each constellation is much more because we need to guarantee a coverage all over the planet. And the satellite that we see right now over Milan are different from the satellites that are right now visible over the United States or over China. Because satellites are able to cover only a specific portion of the Earth at any time. And since the Earth and satellites are orbiting, so they are rotating, there is a continuous variation of which satellite is visible in which specific side of the Earth. It seems easy, so it's just a measure of when the signal is arriving and when it was transmitted. In practice, there are a lot of tools in the world. First of all is the preparation through the ionosphere and troposphere, which is not ideal at all, but that is something related to wireless electromagnetic propagation that is not at the scope of today. So we are not entering into the details of physics. Some of the principle of propagation you should have seen in the courses of physics in the first year of the bachelor, but that's not the point. It's just to mention that propagation in the atmosphere is introducing possible errors. Then there is multi-pattern blockage, which are two wireless specific sources of error that we are going to address in 3 slides. And then the most important problem is to guarantee a perfect synchronization between our device and the satellite. So synchronization of the timing is super important aspect for GNSS-based localization. So where are these satellites? So these satellites are orbiting around the planet following specific trajectories, and on average they are at 26,500 kilometer distance with respect to us. So we have 32 satellites for GPS constellation. This is a visualization of the distance of the different satellites belonging to the GPS solution that are moving single pattern of distance with respect to ourselves, and consider that number here on the left, 26,000 kilometers. So this GPS technology, and in general GNSS, works with a signal that is sent 26,000 kilometers far away and is received by us. Receiving at least 4 of these signals allows to estimate the 3D position and basically allows us to see where we are on our Google map or Apple map or whatever navigation app you are using. So the final use is actually very simple. We just see a circle or a pin in our smartphone, but that is the result of a complex processing and wireless propagation phenomena that started 26,000 kilometers far away from our side. So I said that we need at least 4 satellites to see simultaneously to get the position. In practice, we are on average seeing 8 to 9 satellites. So this is on the right-hand side a figure on the number of simultaneous satellites that we see over Milan in 24 hours. So if we are in Milan right now, we are on average seeing at least 8, I mean a minimum of 6, but up to 12, so overall 8 to 9 satellites. And this means that right now we can estimate our position in Milan by combining 8 to 9 ranging information. So we see only 9 of 32 satellites belonging to the GPS constellation. And since I mentioned that the Earth moves, rotates, and satellites rotate as well, the different satellites belonging to the GPS constellation, so this is one satellite of the constellation, is only visible for a short amount of time. So for instance, satellite 1 is visible only in this period of the day. Satellite 2 is visible in another period, etc. So overall, if you take a vertical slice, you get exactly the right side figure. So this is to show you that 31 satellites are constituting the constellation of GPS then we have all the others, but the focus now is only on the GPS. On average, we use 8 to 9 to measure our position. And there is this intermittent visibility due to the rotation. Let's now enter into the problem, because everything seems to work, and actually it works very well, but what we estimate with the GPS technology is a trajectory that is not exactly the true trajectory that we do. So whenever we see our pin on a map, that pin is always moving, slightly moving, even if we are fixed. And if we, let's say, follow a specific trajectory, that pin is not exactly matching what we are doing. This is because there are errors. So the error is obviously the deviation of the information on our estimated position provided by the GPS and the true trajectory that we are actually traveling on. Obviously, the smaller is the error, the better is the service, and the happier we are because we are following exactly what we want. If the error is too large, sometimes we see in our map that we are in a completely wrong street than the current street we are. That is actually a problem rising, especially in urban areas. So whenever our GPS device receiver is surrounded by tall buildings that limit or obstruct the visibility with respect to the satellite, the quality of the information that we see is definitely poor. On the other hand, if we are in the countryside, in a rural area, we are not surrounded by buildings, so we have a clear sky visibility, and that is the perfect condition for having the smallest error. So the error of position is highly dependent on the environment where we are. Rural area is the best for positioning, so navigation in the countryside provides super accurate information. Positioning information in the urban area is challenged by buildings. And in Italy, we do not have a lot of very tall buildings, while in the United States or in China, the condition is even much more dramatic, because in that cases, you are basically surrounded by walls everywhere, because you only see a very small portion of the sky above your head. So urban areas are the most critical for positioning. And the reason is because buildings are impacting on wireless propagation. So the ideal case where we have our device that is fully, perfectly seeing the sky and has a direct visibility, a direct link with each satellite is only, let's say, the ideal way of describing the GPS service. In practice, a GPS link is blocked by building. So here we see that a signal that is sent from this satellite cannot bypass this building, so it's not received at all, or the signal bouncing off a different medium and receives our device with a reflected path. So we do not have a direct link here, but we have a reflected link. This reflected link is obviously not optimal because it's not providing the true distance information, because there is an excess correction. And overall, this reduces the accuracy of our final position estimate. And the typical sources of error for wireless are these four different phenomena. The first phenomenon is reflection. So whenever a wireless electromagnetic wave is reflected by surfaces, which can be buildings or other types of objects in the environment, the signal arrives at the receiver following a non-direct path. So we may still have the direct path, may also have reflected. And overall, this impairment is making a sort of superposition of different signals from different directions that is not optimal at all. We may have also a shadowing problem. So whenever the direct link is partially blocked by objects, for instance, a wall, the signal passing through this object is attenuated in power and arrives at the receiver with a distortion. Or the signal, the electromagnetic wave can face objects, can, let's say, impinge on objects and being reflected or into different ways, either in a diffractive way or in a scattered way. What does it mean? According to the relation of the object and the wavelength of the electromagnetic signal, so actually it's object size dependent, that specific signal is arriving on the object with one direction and is then diffracted, so it's reproduced and bounced over multiple directions. So the power is basically spread over multiple directions, introducing a reduction of the quality of the signal received at the receiver. Not only in terms of reduced power, but also in terms of extra delay that the signal faces. So these four most common impairments are challenging any wireless propagation, including the GPS transmitter. So just to have a recap, we have a signal that is sent from a satellite at 26,000 kilometers. It arrives to Earth. This type of impairments are actually happening only close to the receiver. So in these 26,000 kilometers part, only the final hundreds of meters are affected by the chaotic impairment that happens to the signal, because only in close proximity to the receiver we have buildings, we have objects that have this type of impact. And this is because we are in a wireless domain, which is a completely different domain rather than a wired one. So in case of wired transmitter, we have a cable that connects the transmitter and the receiver, and the signal only travels in the cable and everything is, let's say, controllable. But in a wireless case, cannot have a control of the cable. We are in the air, everybody's in the air. There is a lot of interference. There are a lot of services that are using the air in the same time as we are using right now. So a lot of multiple systems operating in the frequencies, but wireless is unavoidable for position because we cannot have a cable that connects our device to the satellites, nor a cable that connects our device with any other type of technology. So in order to guarantee worldwide positioning service, we must wireless technology which is subject to environmental perturbation and high interference because it is a shared medium. So there is not a dedicated link, but everything is shared. So that's why wireless, even if it's extremely popular, it must tackle a lot of problems that the wired condition doesn't have, but at the same time, it allows applications that the wired domain cannot guarantee. So overall, the pros and cons of a GPS and GNSS in general technologies have are this one. So it is a worldwide available 24 hours, 7 days a week service that is extremely popular, and high popularity means that the devices have an extremely low cost. So there is not an expensive effort in buying this GPS receiver, and it is also extremely scalable. We do not have to build an infrastructure. We just receive signals from 31 satellites that are orbiting around us, and that's it. So in terms of a user perspective, the investment is basically zero. It's just the receiver, which is few euros. As a con instead is the challenging operation in the dense urban areas, and GPS technology is totally unreliable in indoor because the signal is highly obstructed. So you do not have a clear sky visibility at all if you are inside. So in a warehouse or in your house right now, you cannot see the sky. So the signal enters through the window, but it's not a direct signal at all. It is coming from multipath. So overall, it's not an optimal condition for accurate GPS information. It is a technology that is, especially today when we have war conditions, vulnerable to spoofing and jamming. I'm not entering into the details, but these are attacks that challenge the GPS technology and prevent the receiver to correctly estimate the ranging with respect to the satellite. And these are geographically local attacks that right now are existing mainly in the war areas. And overall, these are possible ways of preventing GNSS service to work properly. In case you need a super accurate, and with super accurate I mean meter level accuracy, the GPS technology is not always able to provide that. So it's not adequate for extremely high positioning. And the last thing is that the design of the 31 satellites orbiting around us is done in order to maximize the accuracy on 2D. While the 3D, so the vertical dimension, is somehow secondary in terms of importance. So the accuracy that you have on the vertical dimension is much, much less than the accuracy in the horizontal. So in case your specific application requires accurate vertical accuracy, then GPS is definitely not the solution for you. Because the geometry of the satellites, so the way we see and the way the problem is designed, which is one device and satellites at 26,000 kilometers, is not optimal for vertical position. I mean, I can spend more on this, but that's definitely too technical, so I'm not entering into the details of why this is not for vertical accuracy, but overall take this as a limitation of this specific technology. So given what we have said so far, where do you think we can use GNSS technology in supply chain? So where can we benefit from a device which it's not a smartphone or it's similar to a smartphone? So a receiver that receives GPS signals and provides the information, a geographic map. Where, why, and how to use it in our supply chain? Which type of innovation can this solution bring? Any idea? So not optimal for indoor. So maybe we need to exclude indoor warehouse management. There are other technologies that perform that. But for tracking in transportation, so understanding the trucks or ships or airplanes, where they are, where they were, is exactly the most straightforward use of GNSS technology in supply chain. So fleet tracking is basically one of the most common services that a lot of companies provided. So these are names of possible companies. So a service that allows you as, let's say, management engineer in a company to open a browser and see, for instance, a map like this, where you see exactly where your fleet is one of the most straightforward adoption of GNSS technology in supply chain. So you see here a web browser, but you can also see in a map, a lot of different objects that you are monitoring, and you see exactly where they are right now. Then you can categorize with colors to find specific criteria, but that's just a software use. The real essence of technology is providing a map information. And this is exactly the most common use of GNSS in supply chain. The second type of topic that I address is instead the alternative, or it's a completely different way of looking at positioning, looking at localization, that is not relying on a global infrastructure of orbiting satellite, but is instead relying on a local network. So it is basically a complementary technology to GNSS. So if GNSS works very well outdoor, what happens when we move indoor? So if we move indoor, we need to rely on sensor network. I mean, indoor is the main use because it's exactly addressing a gap of GNSS, but still you can also use sensor network in local outdoor areas. So in sensor network, we have sensors, so devices that are constituted our infrastructure. So it's actually the equivalent of the satellites for a GNSS. The difference is that these sensors are not orbiting around the Earth. They are static, fixed, installed in specific areas. And these devices are connected with other collaborative devices, which are exactly the equivalent of our smartphone receiver for the GPS technology. So a device that is deliberately sharing information to sending and receiving with wireless with respect to our sensing infrastructure, or the infrastructure can also detect non-collaborative devices. In this case, these devices are passively detected, but still they can be part of our localization in a sensor network. Just to give an idea, this non-collaborative, a passive device can be something that is detected by a video camera or by a radar system, while a collaborative device is instead a wireless device sending and receiving information from the wireless sensing infrastructure. So two different perspectives, but everything is under the same global umbrella of sensor net. And where do we find sensor net? We find in industry, mobility and smart city, surveillance systems, and military and defense applications. And typically, what is the goal of installing sensor network? A goal can be monitoring for detecting intruders, or localizing vehicles, or if you are a vehicle and you are navigating autonomously, you need to understand the obstacles. You'd like to understand where the workers are, where a pallet is, or the occupancy of a specific area. So these are just general examples that are contextualized in different areas. But overall, these are possible ways to describe the deployment of sensors. And now put yourself in the condition of you would like to install a sensor network to address one of these possible use cases. What we have to choose, what are the design choices or the different technological options that we have to deal with? So you can discriminate sensor network technology by productivity. So on the market, you may have wireless or wired infrastructure. You discriminate between where you have to install, so indoor or outdoor. So according to where you put, you may also have different product requirements, because not all of them may work outdoor, just because they have to deal with rain and other environmental issues such as temperature. Then you have to deal with which type of information they provide. So a sensor that provides only ranking, so time information, space, so angle information, or power information. So in order, let's make again the analogy with our human eyes. Do we only need to measure the distance, and angle, only the angle? Power is like the intensity. So if we are using our ears to estimate the distance of a sound, measuring the intensity of the voice, the intensity of the sound is a way of performing measurement and discriminating between close or far away. And most importantly, we need to choose architecture of the deployment. So all the sensors connected to a single centralized processing unit, or each sensor has its own local edge intelligence and is basically able to provide processing on site. Which is the type of sensor? We can have wireless sensor radio frequency, or audio, or optical, such as lasers. And is direction of the measurement. So is the measurement collected at the device itself, or is it based on an infrastructure? Let's specify better this. A device-based measurement means that our device receives the information and computes the measurements and also the positioning, just like the GPS. So the GPS is device-based method. The device receives the signal from 8 to 9 satellites, computes the distance, and measures the position. On the other hand, we can have the reverse process. So we can have a device that is sending the information towards the infrastructure, and the infrastructure collects the information, processes it to estimate the position, and sends back the position to the user. So these are the two different ways of performing the localization process. Overall, a lot of combinations, a lot of possibilities. Choosing which is the best for the specific service is always the most challenging problem. The selection process is definitely based on what you have to do and where you have to install it. So the need of providing a specific deployment with sensor network is because you would like to address something, but you decide what and where to install. So you are not constrained by body. So you need to address something in a specific area in your company. So you deploy the specific technology exactly only in that specific area. Deciding which hardware to according to what are the requirements on the positioning service, basically the accuracy, but not only. And you need to choose the integration with your business. So you need to choose the solution, the provider, such that it is perfectly integrated into your currently existing business. So these are features that are complementary to the previous one. These features are, let's say, related to the technicality and architecture of the solution. These are more related to the business itself. So overall, we have a lot of variables to deal. Let's now enter into the details of how do we perform localization. So which are the type of measurement that we can use to perform localization? And the first type of measurement is the one we have already anticipated with the GPS, which is the ranging. So a measure of the distance of our device, the red one, with respect to the sensing infrastructure. So the device measures the distance and computes the position. So this device measures the distance with respect to this sensor of the architecture, with this one, etc. And then it merges this information to get exactly the final estimate of its position. So this is drawn for a local sensor network of 4 sensors, but I mean conceptually, the visualization also applies to the GPS or to any other type of sensor network. So the important thing is to show you how does ranging information visually appear. So it is a circle around the sensor, and the user, so our device, is located somewhere in this circle. And intersecting the different circles is exactly producing the final results of our position estimate. If it is not range, it can be range difference. So it's no more the distance, but it is the difference of distances. So we have one distance as reference and another distance. So we take, for instance, device sensor 1 as a reference, and we compute the difference with respect to the sensor 1, 2, and 3. Now we do not have a circle anymore. We have an hyperbola, but that's the geometrical interpretation of difference of distances. And the user is located all over this hyperbola. And intersecting the different hyperbolas provides the final user position. The difference is that we need to use one reference. So this means that if we have a sensor network of 4 sensors, we can only have 3 time difference measurements. While in the previous case, with 4 sensors, we have 4 time measurements. A drawback, but it is because this difference of distances is mathematically eliminating the clock difference between the device and the sensor. So it's a way to deal with inaccurate or non-perfectly synchronized devices. So when the user device is not perfectly synchronized with the network, this type of measurement is used instead of the previous one. Another type of measurement is instead the angle. So no more a circle, but the angle is this cone of information with respect to each of these sensors. What is the property of this cone. It is increasing the uncertainty with an increased distance. So look, for instance, here. The more we move far away from this sensor, the more the uncertainty is. So background information is more accurate if the user is very close to the sensor. But overall, the full process is always the same. Measuring the angle of the four sensors of the infrastructure, intersecting, and getting the final estimate of our position. The last type of measurement is instead power. Power is still producing the circular-based information with respect to the sensor. The difference with respect to the ranging is that in wireless propagation, power is logarithmically decreasing the distance. So the accuracy of this information is worse than traditional ranging information. But still, the concept is measuring the power with multiple sensor infrastructure and then intercept them to get the final position. Even if the accuracy with power-only based method is not always good at all. So here we are easily tens of meters of errors because we are not able to get an exact power measurement. And this is why typically power-based information is mainly used not for absolute X and Y positioning, but mainly for proximity positioning. So proximity means you assume or you tell that the device is in the area of one sensor rather than specifying exactly its coordinate. So if this device is connected or is receiving the highest power from this sensor, it is said to be in its proximity and it is located in a specific coverage area. So if this sensor has, I don't know, an area of 100 meters, this device is in a circle of 100 meters, no matter where exactly it is. We know that it is connected with this, so it is, of course, in its coverage area of 100 meters. Having seen the different technicalities or the different way of positioning measurements, let's now see the evaluation. So imagine you have your network of sensors. How do we understand or how do we measure the quality or the accuracy or how does it perform? The metrics are not only used for evaluation, but also for the design. So choosing the trade-off of installation, how many sensors, where to install, how to connect, etc., which measurements they provide, etc., is also design choice. And one metric is scalability. How many devices do we need, at least, to match a specific minimum performance level? Or, on the other hand side, what is the maximum number of devices such that they do not create too much interference between them? Because the more devices you have, the more they simultaneously so they interfere each other, but also the computational complexity of the server. So this, imagine this architecture here, the more devices you add, the more processing load is requested by this processing unit. And there is obviously a maximum number of tolerable number of devices such that you do not saturate the processing or you provide a final position estimate in time. In due time means within a specific maximum latency threshold. Another accuracy is, another metric is the accuracy. How close the estimate is to the real location, and precision. So how much is the system able to replicate the same result in the same condition? Complexity. So the degree of hardware, software, and operating factor of the full localization solution. The robustness, the constant system level accuracy over time. The system must be able to continuously provide the positioning estimates in a reliable and accurate way, even if the technology becomes updated or even if the hardware is aging. The reliability, the percentage of valid estimate, valid positioning results. We need to deal with energy efficiency. So understanding which are the best sensors, if they have to be connected with a wire to the electricity, or if we can use a battery. So in case of battery-based sensor, the energy consumption is strongly related to how many months, years the system can be deployed without intervention on replacing the battery. And the trade-off between how much time we provide measurement and how much we would like the battery to survive is the trade-off for battery-based system. The cost related to the installation, one only installation cost, but also the cost for maintenance and operation. Then we have interoperability, data rate, accessibility, and many, many others. So these are metrics and key performance indicators to account for what to choose a wireless network for localization. Let's now see a very subtle but important difference between accuracy and precision, because accuracy and precision are two different concepts. So a system is accurate if it is able to provide estimates around the real position, while it is precise if the estimates are always consistent among themselves. And look, for instance, here that precise estimates do not necessarily mean that the system is accurate, because you see that these estimates are definitely not around the real position. While this is a system that is both accurate and this is instead only accurate but not precise, because the variability of this estimate is, I think, larger with respect to the real position. Let's now have a break of 5 to 10 minutes, and then we go back with the checking or with the understanding which are the technologies that allow to perform this type of operation. So far we have only seen general ideas, but let's now go on the market. So buy a wireless laptop. Which one do you choose? The technological offer and options. So we will see Wi-Fi, we will see Bluetooth, 5G, and many other technologies that are, let's say, brands that you should know. Okay, so we can start with this second part, which is about the technologies. So which are technologies that we are going to see, where they are applied, how they are applied, and what is actually the main application for each of them. So let's start with the names, because at least the top ones should be familiar to you, while the bottom one maybe are less popular, but still we will see they are super important and commonly used for this. And let's start with the Wi-Fi. So even if Wi-Fi is mostly used for letting our device to be connected to the internet, and it's basically everywhere, that device, that technology is primarily for communication, can be also used for localization. Why? Or simply because if you are connected to a Wi-Fi access point to a router, it means that you are in the area of that router. So the router has 20 meters of coverage. So if you are connected to that router, you are more in radius of 20 meters with respect to it. That's not only the way of performing localization with Wi-Fi, because nowadays the most recent Wi-Fi releases allow to estimate also the time of arrival, so the ranging, and the angle of arrival, together with the received power. So you can actually perform multiple type of measurements for position. Another, let's say, perspective of using Wi-Fi for localization is when the access point, so when the router is not present at all. So in case of infrastructure-less localization, only devices can connect with Wi-Fi and perform localization themselves. So one example is AirDrop or Wi-Fi direct mirroring with your television. So if you perform AirDrop or if you perform mirroring of your smartphone in your television, you are using Wi-Fi technology for communication, for a communication without the router, so a direct communication. But still, the same solution can be used also for position. So Wi-Fi technology for position is not the primary role of Wi-Fi, but it can be for infrastructure-based, but also infrastructure-led. And lastly, let's say the recent advances in Wi-Fi show that it is possible to use Wi-Fi signal as a passive sensing infrastructure. So in this case, you do not have to connect the device. You just use the signals that is sent from the routers and reflected from the environment to passively sense the human and also recognize their shapes. So these latest advances in Wi-Fi, mainly from a research perspective, but also we start seeing some applications on the market, show that it is possible to passively monitor the wireless environment and get an idea and also pretty accurate estimate of the user pose. Why it is important? Because you can automatically repurpose a network of routers for instance, human activity recognition. Imagine, for instance, you are in a hospital, and for sure there are lots of routers. You can use that same network for identifying if a specific patient has fallen on the floor or not. Or you can use the same approach also in a factory. So understanding if there is a worker on the floor because it's not feeling well is an application of this type of wireless signal processing. Another technology is Bluetooth. So it is another commonly used technology, which is pretty, let's say, similar to the Wi-Fi in terms of usability, even if they are completely different from a technical point of view. Bluetooth is more for low energy devices where you do not have to consume a lot of power, mainly for IoT devices. And historically, Bluetooth technology has been adopted for proximity localization. And we can see here in this video that I start now, an example of what does it mean to perform Bluetooth low energy proximity localization.
The phones we carry around are pretty smart, but they...
I don't know if you hear the speaker, the audio of the video. Okay, if you can hear it, it's perfect. No, I mean the voice of the video, not my voice.
They could be a lot smarter. For example, they can connect to a server in another part of the world, but they have no idea that you're in a kitchen, in a conference room, or shopping at your favorite retail store. They lack micro-location context, but now that's changed with Estimote beacons. They use new Bluetooth smart technology, supported by all major mobile platforms, including the recently announced iOS 7 with iBeacons. Put anywhere in the physical world, they broadcast context and location to all compatible phones and smart devices in range. Phones can now automatically pick up the signal and trigger contextual actions designed by business owners. Customers can enjoy a seamless experience with more information about the products that interest them. Photos, videos, reviews, personalized pricing, and even social updates. As they browse through the store, their phones will transition from one item to the next based on their proximity to the displays, enhancing the shopping experience every step of the way. Also, business owners can now benefit from quantitative location data on visits and customer feedback. Better for business and a better experience for shoppers. Smart Retail Solutions by Estimote. Pre-order now at estimote.com.
So this is just an example of customer augmented experience with proximity information provided by Bluetooth. And Bluetooth beacon is the technical term for saying a Bluetooth device that is sending information. So here, the proximity is the localization approach. But since last year, there is the last version of Bluetooth, which allows to perform super accurate positioning with a centimeter level of accuracy, 3D, by installing multiple beacons in the environment and estimating the distance, so the range of the device. This unlocks a lot of potential services in warehouse management, so you can track forklifts or the several boxes, the pallets inside a management plant. Extremely useful for logistics. Or you can apply it in a construction environment where you estimate the position of the different devices and workers as well. Or you can use this Bluetooth technology for smart cities application in monitoring the occupancy of parked slots. So detecting if a car is in a specific lot or not. Here, example from currently existing companies that advertise Bluetooth positioning as their feature. And if you have to, let's say, your properly understand, evaluate the adoption of technology, you exactly see these possibilities. Another technology is RFID, radio frequency identification, which can be an active or a passive technology. Passive technology is basically our credit card system. So you do not have a battery in the credit card, but you just have passive electromagnetic intelligent chip on your card that is sending, reflecting information towards the reader, the shop. Or we can have active RFID systems like the one we use for paying the highway in Italy. And in that case, the devices are the battery. Maybe this type of technology acts with the sensor, so our infrastructure that sends a query signal. The RFID system, the RFID chip replies with the phone. So a query receive mechanism. So in case of a credit card, this is our our paying device at the shop, and the receiver is instead the credit card that prepares the signal. In case of tolling system, it is a device on the tolling gate, and instead our telepass equivalent solution. But where does RFID comes from? Actually, RFID is a perfect example of innovation coming from a practical need. Nowadays, it is used, for instance, in payment and the tolling system, but originally, RFID comes from a defense or a military context. And there was actually this guy which had a real problem, which was identifying if a specific aircraft flying over the United Kingdom was a friend or a foe. So actually, if you look from the ground to the sky, one aircraft is basically equivalent to another one. So if you have a radar system, so a wireless system that is able to detect an aircraft that is traveling over a city, over London, for instance, if it is an aircraft from UK or from Germany or from whatever company, the reflection is basically the same. But what did this guy do? It was basically attaching a specific RFID signature at the bottom of the UK aircraft. So it's basically attaching this equivalent of, let's say, credit card identifier. So whenever you have a reflected signal down to the ground, that signal is carrying the information that is a UK aircraft. It's like you have a credit card that is sending by the information that that credit card is associated to your bank account and not to another one. So a practical need, aircraft identification, brought to the innovation and the introduction, the invention of RFID technology. So it's basically an electromagnetic footprint that is designed intentionally. Maybe you are more familiar with barcode, but I would like to understand, to highlight the difference of RFID with respect to barcode. So the barcode is one code that you can read at a time with a single information or a limited information that cannot be changed easily. And moreover, it's also easily corrupted by dirt, scratches. The RFID is instead allowing a simultaneous reading of multiple RFID cards all together, which are even more resistant to external factors, and the type of data that you can add on an RFID chip is much higher than the limited data you can add in a barcode. And most importantly, you can reuse or update in real time the information of the RFID chip. So high reusability of the same RFID tag for multiple purposes. So you can use it today for tracking, I don't know, a pallet, for identifying a pallet, tomorrow for identifying something else. Simply changing the information you write in the chip itself. And imagine you have a warehouse with multiple pallets. You can attach a RFID tag to identify each pallet, and with just one receiver, one snapshot, have a complete picture of 10 rounds of pallets, because you are simultaneously reading everything together, as long as they are in the reader coverage area. So overall, we can have the application in supply chain traceability, logistics, inventory, retail, warehouse management, security control, jewelry, cosmetics, medicine, and many, many others. But what is, in your opinion, the common feature of these 15 different applications? So these are all use cases that you can think you can use RFID, and actually they are. So there are lots of examples in each of them where RFID has been used, but from, let's say, localization perspective, technical perspective, what's in common among all of these applications? Try to write in the chat a common, let's say, technicality or a common feature. It exists, by the way. So what does library, book management, dose locking, baggage monitoring, warehouse management, etc. have in common? Most of them are indoors, yes, but there are also outdoor use cases, so that's not a common feature to all. So if you pay attention, these 15 applications actually do not need a super accurate positioning information. They just need the information. Okay, it's there, more or less. It's like yes or no, presence, absence. It has crossed the gate, it hasn't crossed the gate. So these RFID applications are more used in localization as proximity identifier, not exactly as X and Y coordinate information. That's because RFID is not able to provide an accurate X and Y information, but is more for proximity. And what I would like to show you now is this video. Obviously not all 10 minutes, but just some ideas. Because this is old, for instance, it's 34 years old, and it is coming from the first application of RFID, Olivet, which was one of the most advanced tech company at that time. maybe the most advanced. So they invented the active badge system. Look what it is.
Well, howdy. Let me tell you about the Active Badge project here at Olivetti Research in Cambridge. Now, the Active Badge project is one of a number of projects we have here which deal with location of personnel and equipment to generate information which makes it possible for computer and communication systems to be easier to use. Now, active badges are personal devices like this one, which we wear. They transmit and receive in the infrared spectrum to transceivers, base transceivers such as this one. And this information makes it possible to define infrared cells which correspond to working spaces. So let's start off with the hardware, and my colleague Tom Blackie will describe the components that make up the active badge
system. It contains infrared transmitter diodes, infrared receiver, 2 push buttons for signaling information back to the system, 2 visible LEDs to provide status information to the user, and a piezo ceramic sounder for sounding, signaling information such as basic paging.
Now, the active badge information is made available to everybody throughout this organization. And one of the systems it's available on is the Unix system. And here is my Unix window. Visited. The 5 asterisks mean that all the recent sightings have been in one place, so that he's static, and in fact he's in my office right here, right now. Mike Adelsey is shown as being away. It is possible to put your own string, your own little words over here, and so it shows that he's not here right now. Other columns indicate the actual position, and other regions indicate what's happening to Olivetti research personnel, what's happening to visitors. I can also click on an individual. I'll click on myself, and it shows that Andy Hopper is at a gathering, in fact, with the film crew and 1 or 2 others, as you would expect, and also shows the various methods of communication that can be used to get hold of me, and my particular list of away entrants. Now, the information for our organization is made available in are rooted in a more sophisticated way.
This X-Windows application presents a hierarchical series of 2-dimensional maps, and at the top level shows the centre of Cambridge. The areas with bold outlines indicate areas with active badge systems. If I select the new museum site, I see 3 areas comprising the computer laboratory system. If I further select on the tower, I see the 10 levels of the tower structure. If I select on floor 2, I can now zoom in and move around. At this level, the map is annotated with active badge sensors and active badges themselves. By using the presence of the active badge as a key, we can control access to resources. For example, I can control access to this workstation. The workstation is monitoring the location of my badge, and when I leave the room, the workstation becomes locked. When I return to the room, the workstation is unlocked. The same sort of technique can be used to give hands-free access through doors. Another application is the management of printer queues. The printer at which a document is eventually printed can be determined from the active badge wearer's location. This can be extended to provide a confidential print facility where the document only appears when the badge wearer is next to the printer. One of the problems with infrared tags is that they can be forged by recording and replay. We've been able to address this problem in the badge because it has a receive capability and an authentication function. The system can generate a random challenge to the badge, which the badge encrypts using password and function.
So we're going to label.
What do we get from this video? Even if it's 30 years and more old, this is a perfect example of triggering automatization with the localization device thanks to the proximity. So not only for activating fax printers, doors, PCs, but also for, let's say, monitoring the status of the employees. And this is really super advanced technology for that time. It may be extremely useful also nowadays because it's not that popular, but still you can see that we can actually, they did, implement all of these features in real systems.
We think of something
And it is
called
actually
the
impressive. Another technology that I would like to show you is ultra wideband. It is another wireless technology that, as the name says, it uses very large bandwidth. Bandwidth, it means the occupancy on the frequency. So lots of I don't have to say the details of what is band for a telecommunications system, but it's the occupancy in the frequency, and it is said to provide them if it's occupying lots of, I mean, hundreds of megahertz or even gigahertz of band. It is a technology that nowadays is becoming installed and available in smartphones and IoT devices. This is just a quick list. Basically, if you are familiar with AirTag and with Find My AirTag of Apple, this is the technology that is used. So when you, let's say, move with your smartphone, checking where the target is, this is actually ultra wideband. This is a technology that is extremely accurate. So this is an example of a test I did, and it is for different companies showing that overall we can have centimeter level of accuracy. But what is the drawback is that the sensing infrastructure, so the device that constitutes the sensor infrastructure, the infrastructure side, have a limited coverage, typically not going beyond 50 meters. In some cases, so if there is no obstacle in between, you can go up to hundreds, but in practical condition, it's 50 meters of coverage, so it's very limited coverage, which means a lot of installation. So in order to monitor an area, there are a lot of manual intervention, manual maintenance to do for installing and keeping the system operative. But overall, so to can install the system, you need super accurate performance. And you can, for instance, track this trolley. So this is a trolley that we manually moved and track all over the trajectory. The line is the trajectory and the dots are instead the estimates provided by the system. And you see that we can quite well follow the overall trajectory. Even if we are in an environment that is a full complete industrial environment, where you see there are lots of metallic objects. As I said at the beginning, objects produce reflection, shadowing, and if they are metallic, they completely block the whiteness of vision. So the industrial environment is the worst environment for positioning because of the metallic presence and machines. But still, even if it's so complex, the ultra wideband has the property of having a large bandwidth and being able to provide accurate. Obviously, if instead of an industrial environment, you are in a laboratory environment where the complexity is definitely less, the accuracy you can have is better. We can, for instance, have 18 centimeter of accuracy in the best condition, which is definitely a super accurate technology. So here, these three different curves indicate an experiment with perfect visibility condition, an experiment where there is a metallic obstruction, so there is not a direct visibility, and the performances you see degrade a little bit, or an experiment where we have people walking around, partially occluding the signal. But the message is, if the environment is not industrial, you can have very accurate performance. And compared to an RFID, the information is dramatically better. But if you move in an industrial environment, the perturbations are such that the performances are expected to degrade a little bit. So if we compare the two with the expected range in a laboratory environment, so the information should lie on a line, the accuracy is very small. While in case of industrial environment, the error is very, let's say, chaotic or unpredictable because there are all of these reflections. But still, we can get accuracy in the range of 30, 50, let's say 1 meter with quite enough confidence. And examples can be adoption for tracking autonomous ground vehicles, quite an accurate position estimate, or tracking these platform experiment. And constructing trajectory of this autonomous vehicle, which had 4 stars simultaneously on top of it every time, and you see that we are super accurate localizing it. Then what I did is let's ask the artificial intelligence to generate an image. So I admit that this is an AI generated image, as you can easily understand, and focus on a smart city context. And what this artificial intelligence said or generated is an image where Bluetooth and ultrawideband are two localization technologies that are, let's say, implemented or expected to bring benefits in a smart city localization context for different indoor navigation, where the GPS cyclist or pedestrian tracking, parking monitoring, as I said at the beginning, or smart pedestrian crossing, or automatic activation of traffic light according to the presence or absence of pedestrian. So overall, this is futuristic, but still possible to construct a vision of smart city where the technologies we have just seen are integrated in a fully connected mobility ecosystem, where food and ultrawideband are mutually. In a vision of a smart city, we can also have another technology that, similarly to Wi-Fi, has been originally conceived for communication, which is the cellular technology that nowadays is in the 5th release. So 5G is the latest commercially available communication technology. But 5G has also introduced native positioning features that targets ideal performances that are very accurate and comparable to ultra-wideband and the latest Bluetooth, but the accuracy is not the focus now. The focus is that 5G is the first cellular technology with native thanks to large bandwidth. So the more bandwidth, the more frequency or frequency you have, the more accurate it is your radio. 5G has introduced the so-called multi-antenna system, so a device that doesn't have only one antenna, but it has multiple antennas able to provide accurate and raw information. 5G is expected to have lots of instant, so high density of antennas, systems with it, which are redundant for multiple simultaneous reception of the signal, just like for the GPS, so that we are able to perform accurate positioning with combination of multiple signals from multiple devices. And overall, the information that is available is super low. But looking at this picture, we see that the intention of 5G is to provide connectivity plus localization for a lot of different cases, which go from drone, mobile robot, automated guided vehicles, what we've seen in the previous video, employees wears connected devices, connected IoT wearable devices, and this, let's say, operation can also work in the context of device to device, so direct visibility without the need of having an infrastructure, just like for Wi-Fi direct. So the concept of Wi-Fi is definitely equivalent to the 5G. Both of them are comparable in terms of operational point of view technologies for joint communication, which is the first primary use case, and position. So just to give the idea of what can be done with positioning, this is a simulation done in the Leonardo campus. So if you are familiar, this is Leonardo Square, this is the Polimi Rectorate. So this is the area around the old historical campus of Polimi, where we have different 5G base stations, so the antennas in the streets. And we have some possible tests to perform. Here we have the receiver, so you can think about our smartphone, located here, which is in the middle of the sport area of the campus. And according to different parameterization, this case refer to the bandwidth used. So large bandwidth means more frequency occupants, and narrow bands means less frequency occupants. So the larger is the bandwidth, the better is the performance. But overall, we can see that at least from a simulation point of view, we can have even sub-meter performance with 5G position. So not now, but in the near future, it is reasonable to expect that together with the GPS service, our smartphone have a 5G or a 6G positioning service that is using the base stations that are in the city to estimate the final user position, using the information that can be, for instance, the ranging. So you see here that this is exactly the ranging concept, where one user is localized by triangulating, so by intercepting the ranging information from different base stations, which produce this circle. And 5G has also implication in the industry. So in a smart connected industry, you can have 5G connectivity and positioning service, for instance, in different contexts, different applications, different use cases with different APIs, but still all addressable care, so in the hospitals, letting the navigation of drones, in retail store for in-store navigation, but also for personalized offer, etc. So overall, you see that use cases are always the same. So use cases that can be addressed by RFID, Bluetooth, Wi-Fi are more or less the same, but they are addressed with different. And this is exactly, I would say, one technology that fits all. So 5G can be, let's say, a super competitor with respect to all the other technology we have seen so far, because it can address all of the use cases, but also guaranteeing the same accuracies, at least theoretically, with respect to all the others. The only difference is that the others are already mature, they are already commercially available. 5G is not yet commercially available so far, but it is expected to exactly address the positioning concept, benefiting from what? Benefiting from almost worldwide coverage, because cellular connectivity is available almost everywhere, or it's going to be available. And it's like repurposing it for. So if instead Bluetooth sensor network or ultra wideband sensor network requires specific installation, 5G can actually exploit cellular operators that are unavoidably already installed in the system. Then, okay, if you need a specific 5G service inside your house, you have to install specific base stations there. But overall, at least for a consumer positioning service, everything comes like in a passive way, just like GPS, more or less. Let's now move completely to passive technology, which is radar detection and ranging. So it is a system that sends electromagnetic signals and listens to the echoes reflected back by the targets. So any object has a specific response to radio frequency impulses. So metallic objects have higher reflectivity, human body has much lower reflectivity, but overall, objects reflect the signals. This is why we have multiple, it's exactly the same concept. The difference is that here, that multiple, so that copies of the received signals are measured by the same device that transmitted in case of monostatic system, while if the reflections are measured by another receiver, it's a distatic system. But overall, the system measures these two ways of signals reflection. So from the transmitter to the object, from the object to the receiver, and estimates its location by measuring the distance and also the angle. A very similar technology is LiDAR, but the difference doesn't use radio frequency information, but optical, so basically laser. So it's just a frequency shift, but the key technological problem is the same. So LiDAR and radar physical concept. The only difference is that radar can somehow also penetrate objects while LiDARs cannot, because light doesn't pass through objects at all. So what is the result is that we have a lot of obstructed areas. So look here, this is a LiDAR on this vehicle, and the vision that the vehicle has for all the reflections from the objects. But look what happens when the light arrives and bounces back from another vehicle behind. What's beyond the vehicle is completely obscured, so it is not possible to see at all in this area because the light cannot pass to the vehicle itself, but it is reflected from all the environment. So even if there is this drawback, overall, this system is super accurate. And the accuracy is definitely I would say, the best on the market, because LiDAR system can have 1 centimeter of error, definitely unbeatable right now. Another solution in passive sensing is camera. Camera that shouldn't be intended like red, green, and blue cameras like our smartphone, but there are different types of cameras. For instance, is the thermal camera, which provide even richer information than the traditional cameras. But no matter what is the type of a camera, the objective of the camera is detect something. They are used for detecting objects. So you see here the detection process, for monitoring possible dangerous areas. So like here we have a specific environment which can be monitored and trigger alarms in case of danger or in case a person enters the area. So cameras that are not only for but also for automatic identification of categories inside the image itself. So here, for instance, we recognize that this is exactly the campus. The camera is detecting box around the human, so it detects the presence of human, and at the same time, it estimates the human position. So it knows where the human is by detecting and localizing it. Overall, these three different passive localization systems, so radar, LiDAR, and camera, are complementary each other. And let's see this comparison also with humans. So let's start from the human. The human, so we are perfect in detecting and classifying objects. We are not that good in estimating the distance, but we are good in detecting the edges, lane tracking, and visibility. I mean, we work very well under visibility. So there is bright light and no dark. Dark, we are very challenged in the and if there is a fog or rain, our peak is as well. While radar, LiDAR, and camera are actually optimal for different tasks. So radar is for the object detection, but not in classification. While object classification is the job of the camera. Distance estimate is perfect with radar and LiDAR. So here we have really centimeter errors, but with camera, it's not that good. Radar under any weather condition. LiDAR, but camera are like our humans. If it's raining, the performance of camera detection is significantly reduced. So overall, what is the message here? If you would like full, perfect, or optimal system, cannot rely only on one technology. And by the way, the most famous example, which is our autonomous vehicles. Autonomous vehicles, typically, I mean, most of them, explore a combination of these three sensors and have overall the best passive sensing system, because they are optimally combining the benefits of each of them. Not Tesla, so Tesla is not using all of them, but all the other companies are typically integrating the information from LiDAR, radar plus LiDAR plus camera. They are good in all of these settings. I would like now to move to a different concept. I mean, not different, it's always related to localization, but it is complicating or is extending, let's say, the problem a little bit. Because localization is snapshot-based service. So you estimate where the user is now. What if the user is moving? So what if instead of localization, we consider the tracking over time? And instead of performing a snapshot localization, so now I localize. After a delta t of time, I localize again. After a delta t, I localize again. What if I can introduce a sort of memory or expectation of what should be the next position, given that I am following a specific trajectory? So, is it possible to integrate the previous estimated location to improve or to assist the current estimate? And the answer is obviously yes. And this is actually the tracking problem. So in a tracking problem, I do not perform only localization, but I perform localization conditioned with what has just happened in the previous seconds or previous minutes. So the concept is, imagine localizing a human walking. And imagine we are tracking its position with either a GPS or with a sensor network, it doesn't matter. So the human is being localized over a trajectory. If I do not embed the trajectory to the history information with the estimation, the user can be anywhere every time we perform localization. But imagine now you are walking. This is your current position. Where is reasonable to expect the next location estimate? Obviously, in the surrounding of the previous one. So you are a human. At most, you walk at 5 kilometers per hour. So if the next position estimate is in 1 second, you cannot be 100 meters away. You can be, I don't know, 3-5 meters around the previous position. So you can force the next position estimate to look for your position in that smaller area of uncertainty. That smaller area of uncertainty is called an a priori information. So you say yourself, okay, combine the measurements, or combine, for instance, the ranging measurements of the next time step and look for the position that is in this area and not everywhere. This is strongly introducing an assistance information to the localization system, and it strongly improves the performances. But how can you do that? So how can you say, if you are a human and you were here, in 1 second you can be only in 5 meters from that position? You need a model. So you need to model the motion of the user you are tracking, which is object dependent. So if you are tracking a pedestrian, you have one model. If you are tracking instead a vehicle, you have a completely different model, because a vehicle in 1 second can travel, I don't know, 20-30 meters according to the speed. So the model is different, but overall you have a model that describes the kinematics of that object. So combining this motion of the kinematic model with the model of the measurement, which it is a ranging measurement, it is an angle measurement, it is a power measurement, you can design a loop where you have an estimate, a prediction of where the next estimate should be, and an update of that a priori information. So you have a loop where you predict, update, predict, that is called a Bayesian tracking principle. So it's a loop over time, continuously update your estimate, combining the type of measurement, so the measurement model, and the kinematic information, rather than performing a blind information. So this is a visualization. Take a couple of minutes to understand what I'm showing. So first of all, these are two different methodologies, but that's not the point. The point is, red means the prediction you do. Green means the update the current position. So this is area where you predict the user, which is given by the motion model and given by the fact that previously it was here. So it was here. So you predict and then you update, so you refine the estimate by reducing the uncertainty area. Then you predict again, you refine as well. So this is a continuous iterative loop where condition somehow the position of the user. And the same concept is visualized here. So at the beginning, these gray points indicate the possible user position. So at the beginning, if you have 4 central users, you don't know where the user is. So at the beginning, you have a blind uniform uncertainty of the user. Then when you start having measures, start reducing the uncertainty area of the user. But look at what happens. The users are increased, the user estimate. So all the positions, possible positions of this brand, increased and reduced, which is a completely equivalent concept than the left-hand side figure, just a different implementation. But the idea of the Bayesian tracking principle is this one. Condition the next estimate with the previous one, enlarging the uncertainty area thanks to the motion model, and then reducing it. Another way of assisting the positioning process in tracking is to condition or to add information on a specific type of measurement or the environment. Let's start with the environment, which is the left-hand figure, which is more easy to understand. So if you are tracking a pedestrian, this is a wall. So if you are tracking a pedestrian in a building and you have the information on the wall, you can force this condition to say to the tracking filter that the user cannot pass through the wall. So you can enforce an environment constraint and facilitate the tracking problem. Or on the left-hand side, you can add information on the measure. So this is the same industrial environment I showed you before. So exactly of this one. So here we have 4 access points, 4 anchors for the sensor of the infrastructure. And this is exactly the top view of that same scenario. These gray areas are the machineries of that area. So the 4 anchors, the 4 sensors, and the machines, and this is the user. This is the time difference of arrival. So one of the type of measurement we have seen 1 hour ago. 4 access points means the 3 time difference of arrival, which in this case are computed with respect to this reference. And the user is located in the intersection of this hyperbola. But as you can see, this hyperbola is not consistent with the intersection of the 2 others one. You see here that 2 intersect here, and this is instead the intersection of this hyperbola with this one, and here is instead the intersection with the other one. So there is an ambiguity here. And the reason is that this hyperbola, so this measurement is affected by non-visibility, so it is obstructed. There is a machine that actually prevented that information. And if you estimate the user position by intersecting this hyperbola, you get an estimate, which is this colored area, which is not perfectly aligned with the user. But what if you work on the measurement? What if you are able to say that that specific measurement is not so reliable because it was obtained in a non-perfect direct visibility condition? So what if you increase the uncertainty associated to that measurement? So if you do that, the intersection now is covering the real user location. So you are using a map of the environment to a priori know if a specific measurement is going to be in visibility or not. And in this case, this measurement, this link, is not direct because there is this obstacle in the middle. So you see here that the red dashed line means that these sensors and the users are not directly connected. There is no visibility at all. So you import this information from the environment, and overall you improve the positioning procedure as position estimate. So these are two different approaches to integrate a system's external information either on the measurement or on the conditional location coming from the environment, which are the more advanced tracking. Where do we find tracking? The typical example of tracking is obviously not only pedestrian navigation, but also vehicle. So let's have a look at this video. So what is this video about? So this is a typical example of tracking. So an object, which is in this case a vector, that is that needs to be tracked over time and space. So this is really the most common tracking problem. But this example is also integrating the tracking concept with the GPS and the global sensor network concept we have seen before. Because what is this video saying? This video says that, okay, tracking in this case is using GNSS technology for outdoor vehicle positioning information plus vehicle mobility kinematic model. So you have a model that adopt for the vehicle. So what can be a vehicle? Okay, a vehicle can be modeled as something that moves more or less at a constant velocity, which is which has a very small lateral movement and a much larger movement on the direction of motion because it can accelerate and brake. So this is an unbalanced condition on motion. And you can use this GPS plus vector motion to track while navigating outside. But as the tunnel enters and approaches a tunnel, what we're seeing today is PS in indoor environment doesn't work at all. So still rely on positioning which can inside the tunnel, your estimate is going to be very, very poor. So what can you do? Especially if this is an autonomous vehicle as it is, and has to travel autonomously in the tunnel with a reliable positioning information. What you can do is inside the tunnel, you can install a local sensor. Here we can have different sensors connected all together that replace the sensor signal which is not received at all inside the tunnel. So the vector switches navigation by receiving these ranging from these sensors, and still it is able to have an accurate positioning information and travel along the tunnel. In this case, the solution we adopted was ultra-wideband, but it can be another technology, but consider ultra-wideband. So GPS for outside, ultra-wideband for inside, and the positioning information still needs to be super accurate without suffering from the transition indoor-outdoor. So practice, I mean, that was an advertisement vehicle, an advertisement movie, but here you see, actually, this is a trolley, this another trolley, another trolley, another trolley here, and same on the right-hand side. And you have the vehicle that travels here. Oops. Here you have a reconstruction of the estimated position. So the vehicle starts moving. These are the estimates of that vehicle. You see that it's location with the ultra wideband inside the tunnel. So this is the network of ultra wideband sensors all connected together, providing the positioning information. Another example is people tracking. Obviously, now the model is completely different. As you can see, we are quite well with high fidelity reconstructing this person running in our port area in the campus Durando. And as you can see, the final reconstructed trajectory is quite well matched with the one that is that hidden. So closing this and description of different technologies and tracking concept, which is augmenting the performance of a pure raw localization system. Let's now see which are the possible, which are the current trends. So I would like you to put in the mind frame of having a system level vision, where at the top we have the service, the application. At the bottom, we have the sensors that are connected all together and that measure something. And then we have obviously something in the middle that connects the surface to the sensing layer. So this is an architecture of the system. From the sensor, communication layer to the final application. Which is, by the way, the concept of industrial internet, which is different from IoT, which is human-centered consumer IoT, where this technology assists or improve the awareness for the human. In the industrial IoT, the human is absent, and the key center is the machine, and industriality is targeted to automatize industrial asset, machine, control system, whatever, by the integration of sensing, communication, and control, targeting to improve the overall monitoring operation of the production. And this is exactly one of the key core domain that 5G is expecting to address. So industriality is really one of the best, most impacted domains by next generation cellular technology. And current, I mean, next in terms of deployment, it's already existing the technology. So this is the comparison of IoT versus industrial IoT. The difference is in area of focus development, degree of application, security, risk, etc. So from smart devices to smart or sophisticated machines, from utility-centric to advanced and robust security, from function independent to integrate with the coexistence already operational system, from low-scale personal network to large-scale network, from user convenience to economic growth, and all the others. And this is really the key cornerstone for the current connectivity in integrated connectivity services and positioning in port areas, refineries areas, manufacturing, construction, mines, etc. With a market that has trillions of dollars of expectation. So the current trend is really looking at 5G as the technology for connectivity and positioning that is going to have a huge market across different sectors, bringing a super significant and dramatic revolution, at least in the plan, guaranteeing interoperability between different systems and ecosystems that goes from providing connectivity to the device of the worker, to the tracking of the car, to the control of the drone, and the control of, in this case, turbine sensors. So this is an example of different types of sensing systems, all integrated together. So environmental, user device, vehicle connectivity, and vehicle drone navigation. So this is a picture that integrates different types of technologies, not only communication and navigation, localization, but also environmental sensing, that can be all fall within the umbrella of cellular system. And this trend is also entering into the industrial companies by bringing a private network that is designed to work only there, only in a specific factory, in a specific manufacturer environment, providing a super accurate positioning service and extremely fast connectivity to all the different types of devices that the company is handed without letting the access to external. So instead of using cellular operator, Vodafone, Verizon, Iliad, whatever, network, nowadays we can have a shift towards installing your local 5G network. So you are working in a company X, you would like to install a 5G network because you have some needs for industrial automation and localization that you need to introduce, well, you can do it now. You ask for the, not that easy, but you can install your own private network of company X, which is only accessible and is only used by the users and device device of that company. And you control everything. So you have a dedicated local network with a deployment as a service, independently managed with all the security graded level of a cellular network that keeps the local data private, and you target the different KPIs of your system that you have to install. And also in this case, I would like you to have a look at this video, which nowadays is 5 years old, but it was the idea that one of the most common and famous companies from cellular industry, which is Qualcomm, generated and produced to show the benefit of having 5G in production, in an industrial production environment. So I would like you to pay attention to what this video is showing, because I mean it's beautiful not only from visual analysis, but it's because it is explaining very well how 5G positioning works, where it can be.
Hi, I'm Balvinder Sachdev, Senior Staff Engineer at Qualcomm Technologies. I'm at our test bed for 5G industrial precise positioning located at our headquarters in San Diego, California. We at Qualcomm have been working hard to develop 5G as a foundation for Industry 4.0 with capabilities like precise positioning, which could help autonomous guided vehicles, or AGVs, navigate warehouses, factories, or retail stores of the future, monitor supply chains, track inventory, and enhance personnel safety, all to help industries attain higher operational efficiencies. In this demo, we're showcasing the 5G precise positioning use case with our over-the-air test bed and the AGV beside me, which has a 5G test device and an inertial measurement sensor on board to complement 5G positioning. Our 5G test bed uses 6 transmission reception points, or TRPs, operating in a deployment-friendly 100 MHz bandwidth in sub-7 GHz frequencies. The sounding reference signal, or SRS, transmitted by the AGV's 5G device is received by multiple TRPs. The AGV's position is triangulated using the uplink time difference of arrival technique, or uplink TDOA. And positioning precision can be enhanced with inertial measurements from the onboard sensor. Looking at the key performance indicators now, we have an absolute accuracy plot that indicates real-time 2D positioning error in centimeters. Below that, we see the signal-to-noise ratio in dB of the SRS from the 5G device received by all TRPs. As the AGV moves along the route, it provides reliable, accurate, and periodic ground truth positioning, shown with black dots, which is then compared with the 5G position estimate in real time using uplink TDOA technique, shown by blue dots, to compute positioning accuracy. Uplink TDOA is a network-based UE-assisted positioning technique where the UE transmits a reference signal and the network measures the difference in time of arrival of the SRS at different TRPs relative to a reference TRP. In both downlink and uplink TDOA, the TRPs need to be synchronized, but the key benefit of TDOA is that tight synchronization between network and the 5G test device is not required. As you can see, we are able to demonstrate centimeter level accuracy in this demo. We are also studying indoor precise positioning in challenging industrial environments. In summary, we've used a deployment-friendly 100 MHz 5G carrier over the air in sub-7 GHz frequencies for uplink TDOA positioning. We complement that with an inertial sensor for centimeter level precision as a proof of concept for 5G industrial precise positioning.
So, maybe most of the technical names are familiar, but it's not the point. The point is to give you the idea of 5G positioning. In this case, it was integrated with the inertial sensor, but that's not the point. The point is that they have, and they show how it is possible to have an AGV, in that case, or an automated grounded vehicle, which transmits signals. Then there are base stations of sensors at the infrastructure side that receives and estimate the position and provide them back the output to the AGV, so that the AGV knows where it is and can navigate autonomously. A similar example is now with our video, which now is more focused on IoT, so more on production process.
Hi, I'm Sam Kotla, Senior Staff Engineer at Qualcomm Technologies. Connectivity and analytics feature prominently in Industry 4.0 as industry leaders seek to improve operational efficiency and responsiveness. 5G is a foundational Industry 4.0 technology because it helps cut the wires for more observable and responsive industrial processes while meeting demanding connectivity requirements. Factories can present challenging radio environments with fast movements and large metallic obstructions. 5G was built for such challenges, and we at Qualcomm have been working hard to advance 5G for industry. I'm at our over-the-air testbed for the Factory of the Future located at our headquarters in San Diego, California, where we develop and demonstrate industrial applications of 5G. The conveyor belt behind me brings objects, black and green pucks, into the field of view of a smart camera, which uses onboard AI to classify them. A 5G device wirelessly connects the smart camera to a G-Node B over the 5G air interface or to another 5G device over a 5G sidelink interface. Object detection triggers from the smart camera are received by the second 5G device connected to the PLC that controls the industrial robot and the gates. The robot must receive control signals from the PLC at the right time to correctly pick and sort the pucks by type, so synchronization is critical. The PLC also controls the gates, which must open at the right time for the pucks to move along the conveyor uninterrupted. 5G supports time-sensitive networking, or TSN, transparently across the network. TSN is used to synchronize the controller with the various sensors and actuators, such as the camera, the robot, and the gates. In addition to TSN, another key requirement is ultra-reliability, which 5G delivers with coordinated multi-point transmissions, or COM, using multiple transmission and reception points, or TRPs. This will allow more robust transmissions in challenging radio environments. Finally, 5G sidelink enables direct communication between the smart camera and the PLC with just one hop. Now, let's look at the demo's dashboard. Since TSN and ultra-reliable communications, or URC, are switched on, we see 0 packet errors and sub-microsecond time synchronization, despite 2 of the 4 TRPs being blocked. When we turn URC off, we see the signal strength dropping since 2 of the TRPs are blocked. The number of packet errors increases due to signal degradation. When we turn URC back on and TSN off, we see the signal strength recover and the packet errors return to 0. But time synchronization is now much poorer than 1 microsecond, which degrades robotic arm accuracy, and many pucks are being missed, as shown by the red beacons around them. Over a 24-hour period, we only achieved 3 nines, or 99.9% reliability with URC off. With URC on, reliability increases significantly to 6 nines, or 99.9999%, giving industry the robustness needed to go wireless with 5G. The new 5G sidelink between the 5G devices has been off all along. From a different angle, we can visualize the activated 5G sidelink for direct device-to-device communications. If the sidelink gets blocked, The packet errors for the 5G side link increases, but the 5G air interface to the G Node B has no packet errors due to URC and can be used as fallback. 5G side links can boost industrial IoT capacity significantly by using precious spectrum resources more efficiently. In this 3GPP standard compliant network simulation, a factory floor has 18 5G G Node B, each with 2 TRPs covering numerous 5G IIoT devices. By default, when 5G side link is off, 2 hop transmissions must be used between 5G IoT devices. The network has enough capacity to support 1080 IIoT devices with 6 nines or 99.9999% reliability. With Sidelink on, 5G IoT devices can use 1 hop direct transmissions between them. 2 hop transmissions are needed only if a Sidelink transmission fails due to a blockage, for example. The simulation shows 5G Sidelink to drastically increase the devices supported from 1080 to 1980 with 6 nines reliability, a capacity gain of 1.8x. In summary, we have demonstrated key 5G capabilities over the air like advanced ultra reliability with coordinated multi-point transmissions, time-sensitive networking with microsecond level synchronization, and direct communications with 5G Sidelink for boosting industrial IoT capacity in the 5G factory of the future, which is why we believe 5G sets the foundation for Industry 4.0.
Okay. Systems, the camera system, the integration with PLC, which is a programmable logic controller of the production side. So they should, an important message here is joint positioning and communication can actually use 5G, which is a wired. So the 5G system, 5G connectivity in a factory doesn't require the cabling of all the devices. Everything is done wireless. And if you think about installation perspective and not only cost, but also the efforts and the problems it may cause, this is super advantageous, which doesn't have word for 5G have communication performances similar to connecting everything with a cable. It's a super fast network, very low latency. It is indeed addressing the industrial IoT cases. All the different devices can be connected together and receive the controls and receive the triggers or send the information in super real time. TSN, which stands for time-sensitive networking, is indeed a claim, actually a category, but it's a category of network that you can consider as a claim to use this 5G technology as a networking layer that fulfills all time-sensitive operations. And in production, everything is time-sensitive, especially if you have robots. And this is everything is all achieved by the 5G technology. So what is the overall summary of this? So these current trends, which are not only focused on localization, but as we have mainly integration of communication and localization in 5G context, it's because the next expected wave, the wave, is 5G in the industry. So while Bluetooth, ultra wideband, consolidated technology already have their market. A company that is looking seriously into the future, and it's possibly a company you have to work with months, it is likely that is looking at 5G technology. Or it's asking, then there are other criteria, but it's at least asking for how to implement a private 5G or how to for connected robots, for connected instruments, and for monitoring all the different things, storage of the content. Maybe also something related to the work. So now, and the reason why I conclude the market oriented is somehow to get you ready on what to expect from the market. So easy solutions, just buy off the shelf Bluetooth, RFID, Wi-Fi, wireless solution. More challenging, but potentially more long-lasting, transversal, multiple report of the technology is okay. Do you have questions so far? If you have questions, let me remind you that the exam, so you cannot bring notes, slides. You just have to answer different questions without getting assistance. And you need to answer in your own PC, so you have to bring your own PC to the examination. We then upload the text of the examiner that you have to download, answer, then apply by uploading it at the end of the examination. But you are not allowed to look fine because of so this concludes today's lesson and all the lessons of the course. In case you have a problem, just drop us emails. This is also, let me also remember that this lesson of today is part of the examination. Thank you. Enjoy your day.